Hello, my name is Cameron Hurd, and this is my report for Lab 2. In this lab, I compared my observational data with two computational models, one which measured just the effects of gravity on the system, and the other included the effects of gravity as well as the drag force. This analysis is important because it will gauge how effective each model is at predicting real-world behavior and can indicate what forces are or could be at play and how they affect the object's motion. The fundamental principle involved in this lab is Newton's second law, or alternatively momentum principle, which states that the acceleration of an object, the change of velocity over time, is directly proportional to the net force applied and inversely proportional to the mass. This relationship is shown here in this example and through the equation shown. So to start things off, I recorded myself dropping a plastic apple, which in this case is my system. I marked positions of the apple's center of mass during the frames that was in motion, and I set the coordinate axes to be centered on the apple's position at time t equals 0, and tilt it slightly since I dropped the ball at a slight angle. I calibrated my data to my height, which is 1.78 meters. You can see that the line that resulted from the data I gathered is curved, which indicates that there is a change in velocity, which then indicates that there's a non-zero net force acting on the system according to Newton's second law. For the first model I have, it is only including gravity. So in this case, we assume the net force is just the force of gravity, and then in turn, the acceleration is constant. For my initial conditions, I set the mass to be this, the position to be this, given that I set the apple to be at the center of the origin of my coordinate axes. I start the time at t equals 0.1 because that is at the frame right before the apple was released, and until 0.7 seconds when it reached the ground. I then calculate my initial velocity at the time t equals 0.1 to be negative 0.19 meters per second. And then for my delta t, I set that based on the difference between the starting and ending time, which is 0.6 seconds, so I made this 100th of that. And here you can see the model that resulted from this. When I put the two graphs together, you see at the beginning the two graphs do align pretty well, but then there is this discrepancy that forms. I estimate that this discrepancy could be due to the camera filming at a slight angle and maybe some errors in how I calibrated the stick. Maybe it's not completely accurate, and the small inaccuracies I made manually plotting the observational data points, accentuated by the object's blur in the video. In future experiments, I'll make sure to properly position the camera and keep in mind that I'll need to calibrate my data when I record my video. In the second model, we have gravity and drag force. In this case, we assume the net force is equal to the force of gravity, which is represented by this equation here, and then the drag force represented by this equation right here. In this case, we assume that acceleration is not constant because as velocity changes, the drag force will change, which results in a differing net force. The initial conditions are the same as the previous model, except with the addition of the coefficient b, which is 0.0029, because it accounts for the first model's end behavior differing from that of the experimental position. So this is meant to align. This is meant to make this model align with the end behavior. Here you can see the models that shown. I zoom in on this just so you can see the drag force arrow as well. When I put all of them together, you can see that the model position with drag, like the model position without drag, is for the most part aligned with the experimental position. We do have a few discrepancies here, likely as a result of human error, but unlike without drag, the model position with drag does align with the experimental position. So what does this mean? Do either computational models predict a terminal velocity? A terminal velocity would indicate that the drag force is equal and opposite to the gravitational force. This would result in them canceling out, and then the F net would equal 0, which indicates a constant velocity. Here, though, in the time span that are recorded, it is hard to tell whether or not each of these models, either one of these models, could predict a terminal velocity. So because of that, I decided to extend the duration to be 5 seconds instead of 0.7 seconds. And here you can see that the model without drag continues to remain straight. The velocity continues to just increase, or I guess in this case decrease due to the direction over time, whereas the model with drag does indicate a terminal velocity as shown. Would the terminal velocity be the same if the object was initially thrown downwards? Yes, it would be the same terminal velocity, however, it would just reach that velocity sooner. For example, if I just throw an apple and is moving at negative 0.190 meters per second at time t equals 0, then it would just reach the terminal velocity sooner because it's already moving. Whereas if it started at rest, it would have to go from rest to the negative 0.19 meters per second, then on to that terminal velocity. Thank you. This is the end.